Where next? Well, that's a good question. We are running out of data. We are genuinely running out of data.
Today we're going to talk about AI with Bryan. Why don't you introduce yourself?
Hello, my name is Bryan Cheong. I'm a data scientist from Singapore and I'm currently working in San Francisco. I previously worked in AI and materials, and I'm now working in AI and revenue forecasting, but I'm happy to talk about other things as well.
And we have Zheng live from Twitter headquarters, day 5 days into Elon's reign. Bryan, where should we start?
We should start with what is being done in terms of the AI. You had two artists before, or two sort of like art adjacent talks about about what AI has impact on them. But it's not about just the artist. It's about sort of what you can do with the technology that is available now. So DALL-E just came out in October. Stable Diffusion came out just 2 weeks after that. Now I've just met with a startup that is using Stable Diffusion to create automatic labels for farmers in India to market their products to richer countries, because these are small little landholding farmers who will never be able to hire a designer, never know what marketing looks like in America or in Europe or in Singapore. And they don't know how to sell their products and have a little bit of a upmarket value. And so now, if you just have a little website, you bring it to them and say, just type in turmeric and whatever, and out comes the label. It belongs to you. You can print it. You can put it on your packaging, and it like 80% can compete with that of a professionally made like designer. And so these are farmers that are earning $2 a day, $2 a day, and they're able to sell their goods to countries with higher purchasing powers. So this is with technology that's already available now. A lot of people are talking about, general AI, AGM, artificial general intelligence that's going to come soon or whatever. But with the tools that you have right now, there's already making real economic impact just 1 month after the tools have been released. And so it's along the lines of we have these new powerful tools and they've been given to the world. Things you create from it belong to the creators. What's next? Nobody knows. And there are lots of low-hanging fruit out there for people who want to try to pluck from it.
So why are these tools so powerful right now?
So it all began in the year 2017 in a paper known as Attention is All You Need. That was the birth of the transformer. That is the underlying basis for GPT, for DALL-E, Stable Diffusion, and so on. And do you want to just talk about what the transformer is? Not in technical mathematical terms, just in terms of what it is. The underlying structure of a transformer is trying to predict what is next. In the original paper, it is about trying to predict what is next in a sentence, for example. So it's like a dictionary that makes a prediction for what comes next in a sentence. That's one example of what a transformer would look like. And that's just it. It's just telling you what to pay attention to and what comes next in what they think will come next in terms of the best output to give. And this underlying structure is what's part of both the text-based things and the image-based things. What we can think of is that when you look at DALL-E, when you look at Stable Diffusion, a lot of the things inside it is the replication of this same structure, right? There are three parts to Stable Diffusion, to any sort of this text-to-image generator. There's going to be an encoder, which is just basically going from a really, really big image down to a really, really small representation of an image. And there's going to be a little denoising algorithm that basically just removes noise continually. And the third part is just a way to encode sentences and words into a mathematical representation. Those are the only three parts of any sort of like image generation powerful engine that you have. And we can talk about what each one means, because right now they sound a bit mysterious, and they shouldn't be. So let's talk about the middle bit. The meat of any sort of AI tool for image generation is this denoising this denoising model. So what Google did with Imagen, it's a model known as Imagen, was they trained a model to remove noise from images. They introduced noise to images, and they told the model, try to optimize for the removal of noise. And at the end of it, they got a model that was really good at removing noise from even like pure noise into real images. So think of DALL-E as something, if given a seed of pure noise, is able to make it into something that is recognizable by humans as a real image. So it's just a denoising algorithm. So far, so good. Great. So that's the imaginative part of DALL-E, of these image algorithms, right? You can give them a seed of pure noise, which has no layers of creativity. You can generate a bunch of them all the time. Just a noisy image, like in the static, for those of you who were born before the 90s, the television screens with the staticky things on it. And then out comes images recognizable by humans as something that's worthwhile and valuable. That's the sort of like the denoising middle bit of it. This was great, except they were working on really small images, because this is a very iterative process and images are really big. So if you want to make it like a 512 by 512 pixel image, that's like, I don't know, is it like 25,000, 250,000? I can't do mental math on the podcast. Number of pixels, that's a lot. And you're going to iterate lots of times on it, and it's expensive. So we don't like that, especially if you want gigantic, beautiful, big images, or even video. Oh gosh, video, that the amount of inputs you want for that. So we want to shrink all that input down to a space that we can traverse. And that's what the first thing comes in, the autoencoder, or is just a way of making a really big image or really big input into something that's smaller. I like to think of it in terms of like a map. If you're going to try to, say, triangulate something on the world, on the Earth, and then you try to use big ropes to try to triangulate the distance of something, that's going to take a lot of effort. Instead, if you just shrink the world down to a map, the map needs to be, a pretty informative representation of the world, be pretty accurate, have like the ratio of distances must be correct, and so on. But if you take a pencil and you just poke a hole in the map, if it's a sharp enough pencil, it's going to correspond exactly to just one hole on the Earth as well. And it'll be a lot easier to triangulate your location on a map versus trying to triangulate your location on the world at large. And so the autoencoder, the VAE, does the same thing. It's a map of the image. It's going to get rid of all the features of an image that it thinks is not important. So like filling the, and then it's going to preserve all the things that are important. What that means in terms of human terms of what we can see is not something that's very easy to talk about, because it's going to be some representation that the machine understands, the human that really doesn't. But you can think of it in terms of, say, if you have edges, or you have particular patterns, or lines, or eyes, or shapes of faces, those would be thought, oh, that's important. We're going to make sure to preserve that in our representation, in our map of things. Other things like smooth surfaces, maybe they don't care. And so the first layer of this image generation thing is just to squeeze everything down into a map that's easy to traverse with your pencil. The second thing is to give a piece of, is to get a machine that's able to turn noise into images that people like. Now, that's two parts. If you have those two parts, you can generate lots of like pretty images already, but they're going to be random. They're going to be like, they're just going to say, oh, you give them random noise, you're going to generate something that looks intelligible. The magic is the last thing, which is just any text representation. So GPT is a way of encoding sentences, English natural language sentences, or other languages, in fact, now, into a representation, a mathematical vector, into something that computers take in. It's just pure numbers. And that is a semantic representation. It represents the meaning of the words. It represents, like, there's something there that says it's past tense, it's talking about a cat, and the cat's chasing a ball, so on. It's just the meaning of the word says in a way that's represented in a vector. And you're combining this vector with the denoiser. So you're training the denoiser to say, not only do I want you to produce an image that is meaningful, that looks pretty, I want you to produce an image that approximates this meaning. So I'm currently giving So to train this particular denoising model, you give them an image of a cat chasing a ball. You give them the sentence, this is a picture of a cat chasing a ball. You push the sentence into the word encoder, into the word part, into the language encoder, and then you're going to noise up the image of the cat with the ball and say, this is a noisy image of a cat with a ball. Now, denoise this and make sure that it is the image of a cat with a ball. And if you do this enough, you get a denoising algorithm that's able to denoise in a way that's biased towards what's represented in your words. So these three things and produce both Stable Diffusion and DALL-E 2, and now image and video. You're going to be making videos using this same exact sort of approach. And I don't want to go to talk about the technicalities of it, right? We're just going to think about it in terms of a game, right? Machines are very good at optimizing things. They're very good at finding the point is like, right, this is going to solve the game. This is going to be the optimal point for a solution for you. You just need to give it the right question, and it'll give you the answer for what is the optimal move to make. Before the 2017 Transformer paper, a lot of people were thinking of image generation in terms of GANs, known as Generative Adversarial Networks. And that is literally a game. You have two players in the game. One is a generative network that makes images, and one is a discriminatory network that discriminates whether this image is generated or it's a real one. And so it's a game between these two players where the generative network is trying to make more and more realistic images to trick the discriminative network. And the discriminative network is trying to improve itself in order to make sure that it's able to distinguish between real and not real images. And at the end of this game, you just throw in a discriminative network, and you have the generative network that's able to create images that look real to the discriminative network. The problem with that is that because it's a game, the computers are like, well, we can just find the cheapest, easiest way to do this, which is we're going to do shortcuts, and then I'm going to just settle on a place that looks weird to humans, but looks fine to the discriminative network. And so it's very unstable, and it was also a very expensive process because you need to have two players and you need to iterate this game a lot of times. And so the introduction of this transformer plays the game, just changes the rules of the game. It says, let's not talk about trying to trick anyone. We already know what nice images look like. The internet is full of them. We're just going to try to extract meaning out of noise. It's like, so you're given something that's noisy, try to make it more meaningful. And just something that's a little bit fuzzy, try to make it sharper, make it more beautiful. Make it more intelligible as an image to humans. And at the very end of all the things, you give it pure noise and say, turn this into something that's intelligible. And that is the creative process, right? You're just drawing things that are meaningful out of the ether. That's the creative process, not just of computers. That's also the creative process of humans. You're just thinking about random things, and then you arrange into something that's meaningful as a pattern. And so we are using computers in terms of what they do best, playing this game to the very optimal point, and we're just making sure that we are doing it in the way that is the least expensive in terms of computation, and in a way that would arrive at a result that would be meaningful to humans in a nuanced fashion.
So, Bryan, when I download the 4 gigs that allows me to run Stable Diffusion on my computer, what is in those 4 gigs?
They are weights. So now the process of creating these weights can cost hundreds of thousands, millions of dollars. You're not downloading any code. Well, you are downloading code. You're not downloading the code for running Stable Diffusion, for training it. You're not creating your own Stable Diffusion. At the very end of all of these processes, at the end of it, you have this bunch of weights, which is the denoising algorithm, basically. And that's it. It's this one layer of weights where you pass in a grid of noise, an image that's just pure noise, pass through these weights, and out comes an image. So this is it. This is the only thing you're downloading. You're downloading like a couple, I think, a few billion, 100 billion parameters that are just gonna,
and these parameters are connected to words.
They are there are two sets of it. One is connected to words. The word encoder thing is connected to words. Mm-hmm. The other one is connected to images, and they're combining together.
Zheng, anything you want to add on that?
You are downloading kind of the distilled output of, um, I guess, millions of compute hours
That's right.
of processing. And this processing is a process of summarization, of taking existing mappings of images to words, and we're going to summarize that.
And so here's the amazing thing, right? This hundreds of millions of hours of, not hundreds of, well, this extremely expensive thing to produce can fit into a thumb drive of 4 GB, because the end result is just a bunch of numbers, basically. And it just so happens that this bunch of numbers works wonderfully in terms of producing images and so on. It's the end result of any of these AI processes is always going to be a lot smaller and less complicated than the whole process is. This is why Stable Diffusion is an open source thing, right? You're able to compete with OpenAI, its own backend engine, because the ability to give to everyone, literally, and have them have Stable Diffusion on their computers is so cheap and so easy. The end result of if you have the weights for the DALI OpenAI things, you are also able to run DALI on your computer. The weights are very small amount of data, and it's all that you need in order to actually create anything based off the AI.
So this is the difference between model and data. This is something related to, you can think about the universe. The universe is very complex, but the laws of physics, you can write it on a napkin, right? And that's the model for the universe. The sum of all images and all image to word mappings is at least not a small one. You can probably fill a few libraries with it. But the distillation of that knowledge is very small. There's not that much information in the world that is fundamental. And I think the process of making these algorithms is to elucidate the fundamental. And then the rest is just details.
Let's talk a little bit about GPT-3 and word algorithms. What's different and similar between what DALI and Stable Diffusion are doing to what GPT-3, how GPT-3 is made and works?
They have fundamentally the building block of the architecture is the same, right? It's you have this transformer. You have the main question that you pose to a transformer is what's important, what comes next. So you give them data, and you ask them what's important in terms of this input, and what comes next. What's the best next output for this input? And they fundamentally have sort of the same underlying structures. This was true even in the past, in terms of like many of the models that were trained for whether it's text or speech or images. They were neural networks. There were some different things. You introduce recurrent networks, you introduce some things in it, but the fundamental sort of mathematics you perform is going to be roughly the same. And this is the reason why you're able to combine the text encoding into the image encoding as well, right? It's the representation it's just a representation of meaning. It's a representation of numbers. You put them together. It so happens that one of them is plugged into an output with like an RGB, like number of pixels that's like 1,000 by 1,000 pixels or something. Well, the other one's encoded in terms of a word, like a list of words, like a list of all the words in the English language or the French language or whatever language. So the input and the output has these like little these vectors that one says it's color in this image, the other in this pixel, and the other is this is the which word this is in the list of words that we have. So, but the structure, I wanted to emphasize that the structure of the architectures are fundamentally the same. You have to tweak things so that one works better for words and one works better for images, but they're not as different as you think in terms of like your eyes and your ears. They're very different structures because one's receiving like images and one's receiving like sounds. That's not true for DALI and for GPT.
I would also add that the reason why everything is using transformer is because the transformer somehow gets us closer to a more optimal summarization method for information. So before we had neural networks that were what were called fully connected or locally connected. So basically, the information you pass, you have this you pass on different layers of information through this machine learning network, and each layer sort of captures different features of different granularity. So in a language setting, you might have the largest granularity is like sentence structure, and like semantic, yeah. And then the smallest granularity might be like individual words or individual sub words or even individual letters. On an image, the largest granularity are like macro features like shapes and relations between shapes. And then the smallest granularity might be minute colorings, minute like margins and stuff like that. The issue with having everything connected to everything else. So basically, neural networks kind of learn this on a stepwise basis. Now the issue is that it's actually like a lot of information. You don't really know what information to pass from one layer to the next. Like if we have a bunch of like small features like lines and edges, what parts of that information is salient to pass it on to the kind of part that understands shapes. It's not. It's kind of like you have to figure out what information is important, and transformers are basically they do this via a mechanism called attention, and attention is basically a little mathematical gate that first computes the importance and then passes the important things to the next level. So basically, it just figures out what's important, and at each level, the important things are being passed out to the next level in a very efficient manner. And so it's kind of like the best way to do this because the entire thing is only built from attention. It's just constantly computing like here's our input features, what's important, pass it on, what's important, pass it on, what's important, pass it on. And at the end you had a very, very succinct representation that basically summarizes literally everything that every layer has determined is important from the input features. And the other reason why it's so powerful is that this importance calculation is simply like a multiplication. It's taking two matrices, two grids of numbers, and multiplying them together. That is extremely easy in like a GPU, or like you take any compute optimized machine, and you can do that super quickly. And it's just a bunch of these chained together. And so you can have these massive networks. You can have like many, you can have tens, hundreds of layers of just computing importance. And that's why you get such good summarizations. Like that's how you can get the super minute, like I can generate a cat riding a unicorn or something, because somewhere within these hundreds of layers, it has understood what is a cat, what is a unicorn, and what are all the minute details. Like not every detail. It doesn't summarize every single cat. It summarizes the important aspects of what makes a cat. And somewhere in those layers, it has done that. And because it's so efficient, it can be really accurate. Because if you have a large network that's not efficient, then you have really bad outputs because it's kind of trying to do too much.
Where next?
Where next? Well, that's a good question. We are running out of data. We are genuinely running out of data. We have a lot of the data that's publicly available is being used for images and text. Where next, I think, would be video. We have a lot of video data that is not. And only just last month, image and video from Google came out, where we were able to generate video outputs. They're okay. They're fine. They're not. They're amazing. Actually, I should be slapping myself. Imagen came out in May, and Imagen video came out in October. We should be like, wow. But reality is that there's a lot of room for improvement. But there are like hours of videos on YouTube, on TikTok, on whatever, and then we can just feed them all in, and then we can make something that generates videos as well. I think that's where's next, because that's where a lot of our data is. Where's next in terms of images, in terms of text, in terms of everything else? I don't know, because we are rate limited by data. These things are really expensive in terms of the amount of data they need. If we are able to find ways of finding more images and generating more text, that's great. But the unfortunate thing is that for the most part, images and text right now are being done by humans, even with the phones being ubiquitous. It's still not enough. These are very, very greedy models that need more data. I am previously working in materials optimization, and so I think there's a lot of room there, but it's not going to be using deep learning. It's not going to be like you plug in I want a material or that that survives in the surface of the sun, and out pops. Here you go. Here's the formulation. Here's how you make it. That's never going to happen because we don't have enough data for that. But I think there's a lot of room for improvement in terms of small data, in terms of creating models that are efficient with small data sets. And maybe the efficiency gains from those can also be transferred to deep learning for things like DALL-E, for things like GPT, so that they're a bit less spendthrift in terms of the data that they need, because we, as I said, we are running out of data.
So yeah, Bryan, let's go a few levels deeper on that. So how would this apply to material science?
Great. So materials are expensive, and experiments for materials are super expensive. You have to have a lab technician mixing things together and then measuring the result of it. And so what a lot of startups and a lot of labs are doing right now is trying to find out how to squeeze as much information as you can out of experiments and out of observational data and out of what we know about how molecules and atoms work. We have all this information. They're all published in papers everywhere, and they're not gathered in the same place. And even like all the data that's made by these large materials companies, these chemicals companies, they're all put in Excel sheets. They're never going to be coordinated, and the only people looking at it are humans. They're not machines. And so the idea, and that's being is to combine all this information in a way that's located in the same place and giving it to something that is able to make predictions based off the data. Let's give you one example. Let's talk about Mitra Chem, which is a company that's based out of California. So the next big thing when the Inflation Reduction Act and everything else is making EVs, electrical vehicles, and you need to make a lot of batteries for that. Batteries are getting more and more expensive because lithium and everything else is getting more expensive. So you want to make sure that the batteries are efficient, they are able to be run over a very long lifetime, and so on. But if you think about how you test battery lifetimes, the way you do it is that you take a battery and then you charge it and then you discharge it. And you do that 1,000 times, and that's going to take a long time, and that's going to be really expensive because you're going to do this. So one composition of the battery, okay, that's fine. Now we're going to test 1,000 more compositions of it, and we're going to test them all like 20 times just to make sure, because we can't just base everything off one battery. And so that's an extremely expensive way of trying to find out what's optimal in terms of your battery composition. And then once that's done, you find your perfect battery, then you can finally give it to all the EVs, and then every car is going to be an EV. So that's going to be great. Even just 1% of savings is going to be like massive in terms of the cost, in terms of the efficiency. But the experiments that you need to go to is just really expensive and takes a long time. Now, this is not as exciting as the GPT stuff and the DALL-E stuff, but you're able to use methods to save. Think of machine learning as a way of saving information from data, of gathering what's important in the data, and using it to the best, in a way that saves, that gathers all the signals out of the noise. So in terms of the experiments, you have all the data, you're measuring it, you're measuring the voltage, and so on and so forth. You're measuring how much it heats up, and you're putting all that data into probably a Bayesian model, and Bayesian is just a statistical approach of things. We don't have to talk about the maths, just in case we don't want you to lose any listeners. So you're just putting into a model and gonna ask the model, can you use all these other data that humans don't really know how to interpret and try to predict using this in terms of what's going to work and what's not going to. So a lot of the times machines are very good at predicting what's not going to work. They're going to look at this like, oh, this little fluctuation in voltage in the beginning, the first 10 cycles of the battery cycling here means it's going to fail 1,000 cycles later. Just throw it out. Don't bother with it. Get rid of it. We're going to move on. So that's a time saving, right? So if you're able to tell in the beginning of your experiments what's not going to work at the end of it, then you can just throw it out and get a new one. And that's going to be a big time saving. And so that's one of the ways that it works out. Think of this in terms of the informational supply chain, right? You are able to create optimizations of these batteries, of these materials really early on, really quickly, really cheaply. You're going to plug it into the factories. They're going to make like tons and tons of these batteries, and they're all going to go onto the roads. And so these are the knock-on effects. So even though the models are really small, even though the models aren't as exciting as generating frogs on a unicycle in a tutu, like you can with, we might see that. You can put that as the image for this podcast. They're going to have really big impacts on the economy in terms of the industries. And I think that's what's next in terms of machine learning. In terms of deep learning, I think what's next is video. So though you have your two answers.
Bryan, how else is the development of AI going to potentially speed up R&D?
That's a
Big question.
Well, R&D has there are two ways that people have been trying for a long time to do this. One is modeling the stuff themselves, and I say stuff because it's very general. You have things like AlphaFold is modeling proteins, and you have things like MyCloud stuff, which is modeling materials. And you have so-called density functional DFT predictors that just predict like little atoms. They can predict, like, say, if your nuclear reactor is going to fail at this temperature. And so these are stuff that has been going on for the last 30, 40 years already. And now but computers have improved dramatically. Our AI capabilities have improved dramatically. And so the idea is that we can plug in these models that we already have from computers into some AI model and some machine learning model. And out comes better abilities to make predictions about how things will behave, even without experiments. That's great. If you are able to predict the properties of stuff, like whether it's materials or proteins or drugs, without expending anything in terms of experiments, that would be perfect, because then you can have AI play games of itself in order to develop something that we wouldn't even be able to dream of looking for. The same way that a human artist would take a long time in order to conceptualize an image that's so out of this world that DALL-E is able to produce. We are going to save the effort of R&D scientists in developing something that out of the way solution.
Bryan, how do you like my startup idea for making GPT-3 for grant writing? Is that too small bore?
So I'm not in academia or policy, so I can't appreciate that. But that's actually one of the big things as well. There are companies that are using AI or using automation to take advantage of bureaucracies, because bureaucracies are massive, and the main barrier to them is human time. If you ever want to write to the IRS, you can. There are lots of things you can do to appeal, like offenses and taxes and so on and so forth. But they take a lot of paperwork. If you can fill up that paperwork, which is mostly quite like well structured with AI, then you win. You're able to beat the bureaucracy at your own game, because usually you think of one tiny human versus this gigantic bureaucratic machine with all the mountains of paperwork you have to search through. If the human is armed with something that's automatic, that's AI based, then suddenly the individual is bigger than the bureaucracy, and just a bunch of individuals can completely overwhelm the bureaucracy. That's one of the value propositions of one startup that's actually, I think, founded by someone from my class at Stanford, called Do Not Pay, which is trying to appeal things like traffic tickets and so on, automatically using forms that are automatically filled out. So I think your idea is amazing, Jordan. If you have a list of all the places that gives out grants, and you have a little machine that just, you click one button and it feels like a mail merge, but it fills out your grants completely with like essays about what you're going to do, you will overwhelm every single grant committee in this country and the world forever.
It wasn't as nefarious as that, Bryan. It was more like, I'm a poor biochemist who's just trying to like fund his lab. But I think there's a bigger point here, is that the sort of established institutions are not ready for what's about to hit them on, many, many different dimensions.
That's right.
Everything from a 7th grade teacher who all of a sudden is going to have perfectly well-written, essays from their students to, I don't know, a news ecosystem that's about to have, completely deep-faked video, which the whole world can do without knowing how to, without someone knowing how to code.
You have stable diffusion on your computer, Jordan. If you put your face into it, or in fact, I think there are some apps online for it, you can like generate photographs, like slightly blurry,
Yeah.
a little bit weird, wonky photographs of, I don't know, yourself in some compromising
Yeah.
positions, or in some in some weird things that incriminating positions as well. So it's this sort of thing that is people just haven't done it yet. At least they have seen, but they can do it very easily.
Yeah.
And let's just say that in terms of disinformation and influence, even without these images, it's been a problem. And so with these images, then how do you fight against that? I don't know. I'm not a policymaker, but you're right. Institutions from primary school teachers all the way to government officials, they're not sure what's going on. I have a funny story. I was working in Taiwan in 2017. That was back. There was 1 month after deep fakes was released in open source, and I was working in the think tank, and I was doing there for machine learning things and so on. And so for the fun of it, I did a deep. I think I did a deep fake for, I can't remember who it was. It was for a Taiwanese politician, and I showed it for them. It was very bad in quality because at the time it was 2017, and I didn't want to spend too much of my Google Cloud credits to train it. But it was able to basically use train the face of a Taiwanese politician onto a video of some old classic like Hong Kong film. And they looked at me and like, isn't this going to be a problem in the future? And I was like, I don't know. It just looks fun to me for now. And I think it might be a problem, especially for we are overestimating how many layers of verification and trust that we have in terms of institutions, and we're underestimating how good these things are, or how
Absolutely.
good these things need to be. So
The other interesting dynamic is like the centralized versus decentralized nature of how these tools are getting developed. Because right now, on some of the bigger batter models like that OpenAI is putting out, they have you can't put in racist slurs, you can't put in, very interestingly, anything sort of like CCP related, and sort of like a whole host of just moderately sensitive things are not allowed. But you download Stable Diffusion, all of a sudden this is open source software, no restrictions. You can put whatever the hell you want. And if the sort of tech ends up evolving such that the open source solutions are almost as good as what the large firms can put out, the ability for there to be some sort of like, I don't know, channeled, my sense is that like this energy is going to be channeled and this tech is going to be channeled in very chaotic and disruptive ways. Whereas if it ended up being a more centralized thing, then you would probably see, I don't know, less disruptive change. Curious for thoughts, reflections on that dynamic, Bryan or Zheng?
let me be clear about this. There is no centralization right now because there's been a big culture of this. The reason why it's called OpenAI, right? A lot of the papers published, they'll give you the full architecture. So if you had enough compute, if you had $1 million to spend on AWS credits, then you can do it too. And remember what we said before, that the end result of all this machine learning training is going to be just a bunch of numbers that you can put in a thumb drive. You can send it in an email, really. So it's a genie in a bottle, and I fundamentally do not believe in the ability to keep genies in their bottles. If stable diffusion is something that's like basically you can, if all these big companies say clamp down and say no, we don't want to release this, a bunch of tech people, well-paid tech people, can say we're going to give $1,000 each. We're going to have 1,000 people do it. We're going to run it in GPUs, and we're going to make something as good, and there's nothing you can do about it. And we're going to release it to the world, and everyone, not just in America, but in India, in Nigeria, wherever, will be free to use this tool. Then that's a genie in the bottle. Once that's out, what do you do about that? You can't take back information. You can't make people unlearn this information. And this is the fundamental part of the technology. This isn't something that you can solve. The only way you can solve this is by like getting rid of all images from the internet, or getting rid of all text from the internet. It is there, and a fundamental feature of this technology is that anyone can do it, and the end result of it is easy to smuggle anywhere. So if you want to fight against that, I think it's a fight against entropy.
Let's talk about Singapore. All right, 2 minutes on Singapore.
Okay.
How's Singapore doing nowadays?
Singapore is doing amazing in terms of the tech they're doing. I just had a dinner with a bunch of people from the open government projects in Singapore who came to the TechCrunch Connect, TechCrunch Disrupt, I think, here in San Francisco. And they're doing amazing work. So this is a group of people hired by the Singapore government building open source projects that are serving government needs. These are open source, which means that anyone in the world can look at the code and, in fact, they can use it. So any government that can't afford a expensive team of six-figure software engineers, they can just take the code and just go in along with the government of Alberta, whoever. And so they're building products for things like tracing like scam calls, for building forms, for government authentication of vouchers and redemption of vouchers. So all these things that sound boring but are part of the essential work of government, and that like uses like millions of dollars of resources for a country like Singapore already, and goodness knows how much for a country like the United States. And just using this technology saves them so much money and so much resource and makes everything efficient. I have two friends. One friend was the lead engineer for Trace Together, which is this app that was the contact tracing app that came out in March of 2020. So basically when everyone was still like, what do we do? And then the Singapore government just said, look, we have a contact tracing app. We wrote it already. Just download it. And the other one was SingPass, which is this one-stop app that I am able to access. If I had tax forms, I can just go to this one app. If I wanted to access things like gift redemption vouchers that the government gives for some reason, I can access it here in San Francisco from my one app on my phone, and there's so much brilliant technology that's going on for any sort of country that they want to use, and I really do hope that San Francisco, California, and the United States actually takes advantage of the fact that you have so many wonderful people that are able to build these products that the governments are able to use. And I'm just so excited for the fact that my country is taking advantage of the talent and technology and moving things forward in terms of building a system of technology-driven governance.
Any final reflections on like how AI is going to change the world?
I think it's so let's put things into perspective, right? Image generation, Imagen came out in May. The optimization for it, the one that said, let's, instead of doing just pure images, let's put it all in a map, came out in October, and we had two products come out in October alone. And right after that, a month or two later, in September, October, can't remember, in September, and in October, video came out, video generation came out. This isn't all in 6 months, okay? It's just boom, it's just really fast. I don't know what's coming next. And even if we knew what's coming next, I don't know what the implications for it are. If you ask people at OpenAI, at wherever, and ask them, what's the implication of this model? I don't think we are able to predict it. It's you're introducing something that's really different, really empowering to a lot of people. And the results are going to be as unpredictable as people are unpredictable, and we're going to be surprised.
Bryan, you got a song for us to close on?
You can close on a since this is China Talk, we can close on like Landlord's Cat. A nice, quiet song from Landlord's Cat for people to contemplate the future of AI on.
Okay. Bryan, Zheng, thanks so much for being a part of China Talk.
Thank you so much for having us.
Pleasure.
我在二环路的里边想着你，你在远方的山上春风十里，今天的风吹向你，下了雨。我说所有的酒都不如你。我在鼓楼的夜色中为你唱花香自泪，在别处沉默相遇和期待，飞机飞过车水马龙的城市， 千里之外不离开，把所有的春天都融进了一个清晨，把所有停不下的言语变成秘密，关上了门。莫名的情愫啊，请问谁来将它带走呢？只好把岁月化成歌，留在山河。我在鼓楼的夜色中为你唱花香自来，在别处沉默相遇和期待，飞机飞过车水马龙的城市，千里之外不离开，把所有的春天都融进了一个清晨，把所有停不下的言语变成秘密，关上了门。莫名的情愫啊，请问谁来将它带走呢？只好把岁月化成歌，留在山河。所有的春天都融进了一个清晨，把所有停不下的言语变成秘密，关上了门。莫名的情愫啊，请问谁来将它带走呢？只好把岁月化成歌，留在山河。我在二环路的里边想着你，你在远方的山上春风十里，今天的风又吹向你，下了雨。我说所有的酒